In the name of God, the Compassionate, the Merciful, Engineering Plasticity, Chapter 5, Plastic Analysis of Bending, Part 7. In this part, we are considering a frame, a structural frame under load. As you can see, this structural frame has members A, B, B, C, and C, D. A, B has a length of 2A, B, C has a length of 2B. The force Q, or the load Q, is acting horizontally and load P is acting vertically. Both Q and P are acting on the middle of the members A, B, and B, C. We want to know how much is the collapse load. In other words, we want to know how much this structure can withstand before failure. How do we do that? Now we can use the same procedure we used in the previous part in order to compute the collapse load. Here we have assumed that fully plastic moment for member BC is equal to a factor C times fully plastic bending moment for members A, B, and CD. Now, in order to do the computation of the collapse load, first of all, we must determine where are the plastic hinges, okay? Where the maximum plastic bending moments occur. In this frame, it is not as clear as it was for the built-in beam. Yeah? So we don't know really where the maximum plastic moments are. But we have some ideas. For instance, we could say that they happen at A, B, C, and D, or maybe at Q and P. So we have to try and many choices and see which one gives a better answer. Okay, so that's what we are going to do. Case A. Now in case A, we are considering the plastic hinges at A, B, C, and D. That's just an assumption. And as you can see, we are not considering the vertical load. We are just considering the horizontal load. In other words, we are saying that the vertical load does not play any role in the failure or in the collapsing of the structure. Taking moments, we could equate the energy or work done, the external work done, equal to the internal work done. Now, work done or the rate of the work done. Here we are assuming that Q is moving this frame with a velocity 1 meter per second. So that is Q is the load times the velocity gives the power or rate of work or rate of energy done. Now, what is it equal to? It's equal to all these hinges. We must consider the moments working on these hinges. Okay, so if I use a pen here, so if it assume this is a straight line, then it has moved that angle, and the moment is around this hinge. Okay, so if this Q is moving 1 meter per second and the distance from here to here is A and distance from there to there is A, then 1 over A is the movement for this moment, which is MA. So 1 over A in fact is theta dot. If we take that as theta, then theta dot is 1 over A. Similarly for B is 1 over A, for C and D theta dot is 1 over a, so ma times theta dot a, mb times theta dot b, etc. So all these theta dots at these hinges are equal because from this geometry. Okay, so we have ma over a, mb over a, or in other words ma times 1 over a, mb times 1 over a, mc times 1 over a, and md times 1 over a. So all these ma, mb, mc, md are equal. Therefore, we could write 4m over a. 4m over a because all of these moments are equal. So that's the answer we have obtained for case A. So how many other cases can we consider? Many other cases, but we should consider only the probable cases, okay? Because that is a probable case. Now, another probable case is that the hinges are formed, for instance, at A under the vertical load at C and D. We call that E. What happens here is that Q is moving with 1 meter per second, but here we don't have any hinges, only here we have a hinge. So these two members, we assume that remain perpendicular to each other. That's our assumption, because there is no hinge here. If this angle changes, it means that's a hinge, but we have not considered it as a hinge. So A, E, C, and D. So we have Q times 1 meter per second. We assume that Q is moving with 1 meter per second. Then P times B over A. So we are assuming that P is moving with the velocity of B over A. If you take the velocity of P as Vp and velocity of Q as Vq, Vq obviously is 1 meter per second. So how much is Vp? Vp times B is equal to Q times A, because there the velocity should be the same. So we get Vp equal to B over A. Okay, you can very easily obtain this. So both Q and P have they play a role in the collapse load. So they are equal to the moments. What? The moments at the hinges. We have again 4 hinges here, so MA over A like before, MA times 1 over A. ME here, ME, obviously P we are saying is moving with B over A. So ME is times B over A, but B over A times 2, because here we have 2 members, okay? And MC 2 over A and MD 1 over A. As you can see here again, we have all these moments at this point. C, MC is moving 2 over A because this is moving 1 meter per second, 1 over A and 1 over A. So that's because we have a hinge here and all of these members, so it's moving 2 over A because A is from here to there, so that's 2A. So if it is moving with 1 over A, it must be moving with 2 over A. And here we assume that ME is C times M, as we have said before, and all of these are equal. So Q plus B, P times B over A becomes equal to a factor times M. Of course, this M is MP, the plastic moment, fully plastic moment. Now, another case we can consider is this case, in which we are only considering load P. We are not considering load Q. we say that this does not have any effect on the failure of the structure. The only effect is due to P. So we could take these three as hinges, plastic hinges, and we could write this equation. P times, here again we suppose that it's moving 1 meter per second because we have omitted this. So this is 1 meter per second. P times 1 is equal to MB, that distance is B, and ME obviously, because these two members are moving, this one is just like the built-in beam that we considered before, and MC over B, and so we get P equal to 2 times 1 plus CM over B. And for case D, we are considering only force Q, and in this case we are considering 3 hinges here, because before we considered Q only, but we just took the hinges at these 4 points. But here we say that these 2 are solid, remain solid, but here we get some hinges, 3 hinges. So let's do it with this. Then Q times 1 meter again per second. This one also is just like the built-in beam. So we have MA over A, 2ME over A, and MB over A. So we get 4M over A. So Q is 4M over A. We could consider other cases, but here I have just demonstrated 4 cases. Okay, you could consider 10 cases or more. But these are the 4 probable cases. And if we put some numbers here for the Q in terms of P, this parameter C is equal to 1.5, and B over A take it as 3, because we want to get some numbers. So for case A, we get P equal to M over A. This M is fully plastic moment. And for case B, we get P equal to 1.4 M over A. Obviously, when we have P, we have Q as well. And for case C, we get 1.67 M over A. And for case 4, which is D, we get P equal to 2 M over A. Look at this. Okay, here we have different values for P. Now, which one is the correct one? Now, this smaller one is the correct one. Here we use the lower bound, we call it. Okay, why is the smaller one? Because we have shown by this case that if the load reaches 1.4 M over A, the structure fails. So if we use others which are greater than that, it means that failure may occur, because any of these cases are possible. So we take the least value as the design value. Okay, obviously this is a calculation based on the collapse load, so we can use a factor of safety as well. So that's our design value, and we can easily obtain this, as you can see. If you wanted to do other formulation and computations, it would not be possible to do it analytically. You would have to do it computationally, numerically. You would have to use finite element method to solve such problem. Therefore, this is the correct answer. Okay, that's the correct answer. The least possible value is the correct answer. You can see that 1.4, 1.67 are very near to each other, but maybe you can find another case that is smaller than this. That would be the answer, but you can find it. That's the least possible load that could cause the collapse of this structure. A similar example to the previous one is this frame, okay, except that H is applied at the top of this member and V is applied at the middle. So we call these hinges or points, joints 1, 2, 3, 4, and 5. Joint 1, joint 2, that is where the vertical force is acting, that's where the horizontal force is acting, and joint 4 and 5. And this distance is 2L, as this distance is H. And we are saying that the MO is the maximum plastic bending moment which can be applied at these joints. That's the fully plastic moment. Now again, like before, I'm going to consider a few cases. Here I want to show you what the interaction diagram is. Okay, I want to introduce this interaction diagram for these portal frames. Now in here again we have considered a case like the one we considered before, and clearly M1 times theta, M2 times theta. In this example I have used work instead of rate of work, so theta instead of theta dot. So that's energy done or work done, Newton meter. M1 theta, M2 theta, theta is in radian, that is in Newton meter, so that's work or energy. And is equal to this load times H times theta, because that's the distance moved. Yeah, I just show you here with this pen. That is the distance. Okay, so that is theta, and that distance is this distance, which is H, times theta is this distance. So H times theta times H gives us the force. Therefore we could write this as 4m0 equal to H times H, and we get H times H divided by m0 is equal to 4. Also here I can use another diagram, another case like this. We considered this case for the previous example as well. So M2, that is M2 times theta, M3 obviously times 2 theta, and M4 times theta. So we get VL over M0 equal to 4 because V times L. Yeah, that is L theta. L theta is the distance moved. And for the third case, we consider both of them, H and V, and we put it like that, and M1 theta, M3 2 theta, and M4 2 theta, and M5 theta. Okay, 1, 3, 4, and 5. This 2 remains perpendicular. So H times H theta and V times L theta. If we simplify this, we get VL plus HH divided by M0 equal to 6. So we obtain 3 solutions here. Okay, I'm going to use these 3 solutions in the interaction diagram. In the previous example, I said that we get the least value as the correct one and use that for design. But here I'm going to use the interaction diagram instead of the least value. And what is the interaction diagram? Interaction diagram is something like this. You see, I have used this case, that case, and this case. 3 cases. Okay. The relationship between H and V producing plastic collapse is shown graphically. That's VLM0, HHM0. Okay, because I've got VLM0 and HHM0, and the combination of them is 6. Each of them are 4. So here, that's 4 for VLM0. That's 4 for HHM0, and I have plotted VLM0 against HHM0, and then that is the combination of both of them. So if I had another solution, I could have drawn the lines as well. So the relationship between H and V producing plastic collapse is shown graphically here. Now the mode of collapse associated with each linear segment. That's one mode of collapse, another mode, and this is another mode. The diagram being as indicated. Such a diagram, known as the interaction diagram, is always a convex locus enclosing the origin. So it's a convex. Any combination of H and V represented by a point inside the diagram constitute a safe state of external loading. For design purposes, therefore, for this kind of a structure, if we consider point here, there, or there, we are in the safe zone. But if we go out of this boundary, then collapse occurs. For instance, if you consider some point, let me use the pen here. Let's consider this point here. Okay, this point here. I consider this point here, and so that is the VL over M0, and that is the HH over M0. And you can see we have, for instance, if you go like that, or if you go like that, you have some distance from this boundary. Or maybe if you take the position from here to there, then you have some factor of safety here. I mean, the distance from these boundaries gives you a factor of safety. So that's how you choose your design point. Okay, one of these points here, anywhere, is a design point. You can go very near to the boundary, or you can stay away from the boundary.